Good evening, everyone. Welcome to another session of Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber-Physical Systems, IISc. Today's talk is by Arun Padakandla, and he'll be speaking on PAC learning on a quantum computer, a new ERM algorithm, and sample complexity bounds. Arun Padakandla is a tenure-track assistant professor with the Department of ECS at the University of Tennessee at Knoxville. He holds a PhD from the University of Michigan at Ann Arbor and a master's from IISc Bangalore. Following a brief stint as a research engineer with Ericsson Research, San Jose, he held a postdoctoral research fellowship with the NSF Center for Science of Information at Purdue University. Arun's research interests are in quantum information science. Before we move on to the talk, we'd like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Arun directly. Over to you, Arun.
Thank you. Can you all hear me?
Yes.
Okay, great. Yeah, okay. Thanks to the organizers for inviting me. It's a good opportunity to present my work. So feel free to ask questions along the way. I'm not packing too much material. The idea is to convey, the goal is to convey the ideas. So feel free to ask questions. And okay, so I'll be talking about PAC learning on quantum computers, and the the goal is to present a new empirical risk minimization algorithm, and indicate some sample complexity bounds. So this talk lies at the intersection of quantum computation and statistical learning theory. And what I've observed is that my audience, either it's in the papers or it's in the talk, is either they are experts in something else and they are interested in this talk, or they're experts in statistical learning theory without much idea about quantum formalism, or they're quantum physicists without much idea of Rademacher complexity, VC dimension, and all that. So what I'll do is I don't want to I want to take everybody along. So I'm going to have a little bit of a preview to both parts, and so that everybody kind of understands. So having said that, let's get to the outline. So what I'll do is I'll first kind of refresh PAC learning. Identify a few key elements that we take for granted, and it'll kind of blow up in the face of quantum learning. I will then go on to formulating a problem of learning on a quantum computer, followed by kind of presenting the quantum ERM algorithm. Okay, so a little bit about this talk. So this talk is very pictorial. The goal is to convey the ideas. I'm not intending to convey the technicalities and the correctness of the proof. That's not the goal. The goal is to kind of convey the ideas, and there are a few key nice ideas which I will kind of communicate. So it's very pictorial. You don't have to read text on the slide. Just kind of listen to me, follow through, just look at the pictures, and you will get the idea. So just kind of a broad level perspective. So this is a continuing thread of work. I started this with a postdoc at Purdue. His name is Mohsen. Then I started to work on it independently because he got busy in something else, and then I did a good part of the work, and then later I now got a collaborator in another theoretical computer science person, Abraham Magner. So, and this is published in A-Stats recently. Okay, so I'll just refresh PAC learning. It's good for everyone to just kind of get to know my notation. So what better scenario to present PAC learning than the current scenario we are in? So think yourself, you're a machine learning specialist. You're hired by the Karnataka government, and you have to do some data analytics for them. And think of this, the health secretary of Karnataka comes to you and says, hey, there is a respiratory virus that is spreading, and I need to budget resources. I need to allocate resources in different places. I need to know how much oxygen to where to pump the oxygen, where to establish field hospitals, who are going to be vulnerable, who need help, right? So I have health data of the people, and I want you to kind of tell me, kind of fill up the table. So you have question marks on the right. Okay, you don't know the right thing, and you kind of want to fill up. So the right is not clear to me. The right is all empty, and you have to fill that right table for me. Okay, and what he says is, hey, I have some data I have some training data because the airport in Bangalore has already seen some people come in, and I have seen that some people have already suffered, and I can figure out how many of them are suffering and stuff like that. So can you use that data to kind of fill the table up? Okay, so the up table, think of the right side blue part of the up table having all question marks. You don't know it, and your goal is to kind of fill that up, and you have to use the table at the bottom to kind of fill the table at the top. Okay, so this is kind of a canonical learning problem, and what I have on the left is features or data or input, and what I need to fill on the right is your labels, or you have to come up with inferences, or what we call also as output. So so this kind of gives you a good perspective of a learning problem. So let me go ahead and kind of get into this problem. So what is a learning problem? So you have an input space X, some feature space. You have a finite set of labels or outputs. That finite set could be either just binary, it could be a bunch of labels that mean something to us, or it could be a continuous set, whatever it is. And you have X, and there is an unknown probabilistic relationship between X and Y. And the broad problem of learning, in some sense, is to learn this underlying relationship, often through samples of the data. So you have some samples of the data, and you want to learn this underlying relationship through samples of the data. Okay, so so how do you learn this relationship? What do you do? So what we are looking for is a predictor. It's a function. It's a good function that goes from X to Y. It takes a feature and it gives you a label. So that's kind of the goal of the you have to find a good predictor. And how do you do that? Well, any function is a candidate predictor. So what I do, I equip my computer with a bag of predictors, what I will call a concept class. The learning theorists refer to this also as a hypothesis class. I'm reserving the word concept, and I'm reserving the word hypothesis and H later on, because it will be a Hilbert space for me in the quantum setting. So you equip your computer with a bag of predictors, and the goal of a learning algorithm is to fish out an optimal predictor from within C. Okay, so that's the goal. Now I have mentioned what is an optimal predictor, but I've not kind of defined it. So let me get into a little bit more details. So this is what the learning algorithm should do. Should essentially fish out the right predictor for your data. So so think of the actual scenario on the left. You have this table, you have the feature set. There are question marks on the right, which you have to fill up. So you have to find a good predictor to fill up these question marks on the right. So your feature set is you have 4 attributes, the ancestral origin, the blood sugar, 2 more attributes. So your feature set is a Cartesian product of 4 sets, and your label set is the COVID virility, and you have some training data. Okay. So let's now identify what does it mean to say an optimal predictor. So there is this unknown distribution. So it's an unknown underlying distribution modeling the relationship. You don't know that. Let's take a loss function, a non-negative valued function that kind of gives you the loss between 2 labels. And if I take a predictor, remember I told you that any function is a classifier. So suppose I take a predictor or a classifier, I can associate with it what is called the true risk. The true risk is essentially the expected loss of the risk if my data was coming from P. Okay, so this true risk is a function of P, and you don't know the underlying distribution. You only have this bag of predictors, and the goal is to kind of get to the predictor with the least loss. Okay, so let's kind of quantify that. So on the right, so given a concept class C and a distribution P, I can choose that predictor with the least true risk, right? And I will denote that least true risk as the script, calligraphic L of C comma P. Okay, so it is the loss of the best predictor if you knew the distribution P. So if you knew the distribution P, you would just go to your bag of predictors and choose this, the one that kind of minimizes the true risk, and you'll be happy with that. But what's the goal of the learning algorithm? So the goal of the learning algorithm, in some sense, is you're oblivious to P, and your goal is to identify a predictor F from your bag of predictors whose empirical risk is very close to the least that you can possibly get. Okay? So that is kind of the goal of the learning algorithm, at a broad level. I will highlight one key point that many people will take for granted, but something that I'll again do it with examples. So the idea is the following. So your learning algorithm must be universal in the sense that suppose I input the training data from a particular data set. Okay, suppose I enter the training data from Karnataka. Okay, so I take the people from Karnataka. They have a different ethnicity. They have a different COVID virility. I enter the training data coming from Karnataka into the learning algorithm. This learning algorithm should fish out an optimal predictor for the Karnataka data. Okay. Now, if I enter Kerala data, so there, the ethnicity is different, their COVID virility is different. If I enter the training data for people from Kerala, my learning algorithm, the same learning algorithm, must pull out the optimal predictor for Kerala. Okay, so that is what we call as distribution-free learning algorithm. Obviously, you cannot get a universal learning algorithm, but if you choose your concept class nicely, and if you have some idea of how you design your concept class, you can actually do this. So this is really the key element in the learning algorithm. So I'm actually formalizing this in the next few slides, but I'm not going to go through this because if anybody is interested, I can go over it, but I'll essentially tell you the key ideas. Okay, so now, suppose you are tasked with this goal of designing a learning algorithm. What would you do? You are given a bunch of data. You are equipped with a bag of predictors, and your goal is to kind of identify a good predictor. What do? Well, the most natural thing you would do is you would first kind of pick a function. You would pick a function from this. You have your training data. So you run your function, your candidate predictor on your feature set. You get a bunch of labels for that. Your predictor, it may be bad, it may be good. It'll give you a set of labels. You compare that with what is actually true. So what you do is you compute the empirical risk. So you compute the function f on your features. You you compute the loss with respect to the true labels, and you just look at the empirical risk. Okay, and what is the most natural thing to do? Well, in some sense, it looks like this is all that you can do. You would go and choose that function in your concept class that minimizes the empirical risk. Okay, so this is what is referred to as the empirical risk minimization rule. Very simple, the most natural, and really what you have to show is that in some sense this converges to the optimal predictor no matter what the distribution is. So you choose a different distribution, the same empirical risk minimization rule should be able to fish out the right predictor for you. In other words, this the f that the minimizing f should be actually good for the distribution from which the data is coming. Okay, so that is where you kind of use your concentration bounds and stuff like that, and your structure of the prediction, the concept class that you have used in some sense show this. Okay, so so we will actually come to this, and this is a very canonical algorithm, and a lot of early statistical learning theory was aimed at kind of understanding this empirical risk minimization rule. How do you build a good concept class so that I can pick up an empirical risk minimization rule? I mean, I can pick up the right concept, right predictor from this bag. So really the hard part is, see, you have to compute the empirical risk for every function in this class. That's a computationally difficult problem. So how do you structure your concept class so that you can efficiently compute the empirical risk and choose the identifier? Okay, so that's where a lot of your neural nets will come in and stuff like that. Now, this is very canonical, but there are things we take for granted which will kind of blow up in the face of quantum. So I'll go to kind of tell you that. So we'll make a few, we'll kind of make a few observations on the few things that we saw so far. So the first thing is, with classical data, learning is a function learning problem. Essentially, Your concept class is a bag of functions, and you want to learn a function. That's kind of your broad goal. As you will see in quantum data, this will change. You're not going to be learning functions anymore. You're going to be learning what is called measurements. So I'll come to that. The second thing, the algorithm that we talked about, the empirical risk minimization algorithm, what did it do? It took each xy and it used that to evaluate the empirical risk of every function in my class, right? Now, it turns out this is very, is very simple. It's taken for granted in classical, but you will see things will change in the quantum. So I would just like to, kind of keep these two observations with you in your mind as we go along to the kind of the next part. So now I'll come to quantum computer. Okay, I'm guessing that some of you might not know the formalisms, so I'll actually tell you the basics of what quantum computer is, how does it do the operations, and how we can use that to formulate a problem of learning, and how does this empirical risk minimization rule manifest in the quantum setting. That's kind of the broad direction I'm going. I'll pause for if there are any questions, any comments, any thoughts. Okay, so let me go ahead. So what is a quantum computer? Okay, I'm just going to do some very basics. So on a quantum computer, I mean, a good kind of a cartoonistic way of thinking of this is the following. So data is encoded by preparing subatomic particles with specific attributes. Okay, so the way I think of it is, you take an electron, it has an axis of spin, you orient the axis of the spin, and you encode data. So on the right bottom, I have taken 4 pictures. I mean, I've taken 4 different electrons whose axis of spin is oriented in 4 different directions, and you can store 2 bits on that. Okay, it's kind of a nice way to think of it. Or what you can do is you can modify the polarization plane of a photon. Okay, that's how you kind of store data. I mean, in some sense, in a way to think of it. Okay, great. You found a way to encode data, great, but what is the difference? What is the essential difference? So the essential difference is the following. Registers are macroscopic and particles are microscopic. And what registers are what are observables, okay? So you can observe the state of a register. You can, kind of read the value out and nothing will happen to the register. But particles are extremely, I mean, this is essentially the Heisenberg uncertainty principle, but in quotes, they're extremely flimsy, or, they're very, very sensitive to any interaction. So I'm going to, kind of write that down. So state of a register is observable. You can read contents of the register without altering it. But the particle is not observable. Any interaction alters it. So, literally even a benign stare at it kind of alters it. And so this is the key. And the entire, formulation of a quantum computer, how you do operations on that are very different from the classical computer. And so through the rest of the talk, so we'll have to understand how a particle behaves. If we have to do any computation, any learning on a quantum computer, you need to understand how a particle behaves. So the behavior of particles is governed by the axioms of quantum mechanics. That's the first thing. I'll just kind of give you a brief idea of what I will need to be able to explain the problem of learning. And throughout the talk, I will kind of, interchangeably use this subatomic particle and quantum states. So I might refer to a prepared subatomic particle as a quantum state. I think there's a question. Somebody has a question? Does somebody have, yeah. I'm not able to hear you.
Okay,
it seems like it's not muted. Okay. Okay, I'll keep going if there is no question. Okay, so now let's come to the problem of formulating learning on a quantum computer. So, remember we had 2 things on a learning problem. We have features and we have labels. So where is now my features going to be? Where are my labels going to be? So remember I told you that registers are macroscopic, particles are microscopic. We cannot observe a particle. So the natural thing to do is to kind of encode a feature on a particle. And because labels are our inferences, we want to be able to observe them. So what I'll do is I will model the labels to be stored on classical registers as before, but features will be encoded on subatomic particles. Okay, so just like you're given a set of features and you have to predict a label for that. Now on a quantum computer, think of the following. Somebody has encoded the features on subatomic particles. So they have kind of prepared the subatomic particles with some characteristics. And you have to extract the label that is kind of in their mind, okay, or that is the truth with that. So that's kind of the modeling I'll go to. And the next topic is to kind of tell you what is, how does the quantum particles behave to be able to go to the, to be able to understand what is a predictor. Okay, so remember, so let's go back to our learning. Okay, learning on a classical computer. What did you do learning on a classical computer? Well, we had features. So I have denoted these features in terms of these registers. So essentially, you have a bunch of features, and each feature is associated with a label. So this red and blue are kind of your labels. So you had some training data. So you had a bunch of features and labels. Now that was given to your learning algorithm. The learning algorithm had a bag of predictors with it, which were essentially functions. And what it would do is it would use this training data and pull out a function or a classifier or a predictor. And that function could be used to label this feature whose label we do not know. So it could be used to compute the label of this function. Now what happens in a quantum computer? So I have now given you the formalism. I've just formulated the problem. So now my features are prepared electrons, prepared subatomic particles, or what I call quantum states. They're associated with certain labels, and those labels are stored in registers. Now, what is my learning algorithm? What is a predictor? What is a concept class? What should my learning algorithm do? And how do we label a quantum state, right? So all of these basic questions are also now up in the graphs, because the model of computation is itself completely different, right? So we need to kind of go back and revisit, how do we model this? How do we, remember in classical computer, we model everything through sets and functions. Now, what is the modeling on, with quantum particles? That's kind of the question. So so that's where I'll be going. I'll be kind of telling you, how do we mathematically model these objects, and what is a predictor, and how do I come up with an empirical risk minimization rule? That's kind of the broad picture. So let's do some very basics of quantum computer, or in some sense, essentially understand how quantum states behave. So if you look at classical, right, I'm going to connect to what we know. So if you look at classical data or classical computer, everything is modeled in some sense through sets and functions, essentially discrete mathematics. If you go to a computer science department, they'll essentially do courses in discrete mathematics. And what is that? You essentially look at set theory, look at functions, probabilistic distributions, and what is your state space? Where does your data live? Your data lives essentially in a finite set, okay? And you could, if you ask me what is the state of a register, you could tell me, well, the state of a register is a particular value, X taking the value in the set X. Or you could tell me, hey, it's random, so I have a distribution Px that models the state of this register. If that distribution is singular, it's a deterministic, it's kind of a deterministic thing. If it's not, it's a probabilistic distribution. What happens in quantum? So the state space of a register, the state space of a quantum particle, of a prepared quantum particle, is what is called a Hilbert space. Okay, what is a Hilbert space? No big deal, just a complete inner product space. Okay, so if you actually look at it from a mathematical point of view, they essentially focus on infinite dimensions, but all of the ideas can be kind of understood through just Cn. So essentially think of this as a complete inner product space on the complex field. If you are comfortable with the real field, you can just look at it from the real field also. It's totally fine. So I will kind of fill up the table on the left. for each one of them. So what is the analog? What should you go and study if you want to study quantum states? You'll have to go and do a little bit of function analysis, a little bit of Hilbert spaces, linear operators, linear algebra and stuff like that. What is the state space of a register? So of a quantum particle, it's a Hilbert space. So just as you say, okay, the register takes a value in X, you can just you can think of a prepared particle to be taking some it lives in the Hilbert space. What is a distribution? The analog of a distribution is what is called a density operator. So remember, why am I saying all this? Because remember, a feature, the characterization of a feature, unknown feature, is an unknown distribution, right? So now if you give me a particle, what is the characterization of that particle? It's going to be a density operator. You give me a feature encoded on a particle, what is the kind of the modeling of that? That's going to be a density operator. What is a density operator? Don't get kind of taken aback by these names. Essentially, it's just a linear transformation. It's a positive semi-definite linear transformation with unit trace. What is a trace? You just add the eigenvalues, or you just add the diagonal elements. So you take a positive, you take a positive semi-definite linear transform whose trace is 1. It's called a trace class operator. That is what is a density operator. Now, it turns out a density operator is the analog of a probabilistic distribution. So if you want to study random variables in quantum, you'll have to go and study density operators. Not a big deal, but I'll just introduce these things so that you kind of get a feel. So, so let's go back to our particles. So essentially what has happened is that if you were encoding 0001, 1011, on 4, if you're encoding that on a subatomic particle by just kind of, orienting the axis of the spin of the electron, what you're essentially doing is you are you are defining some density operators. So if you ask me, okay, how does this particle that I've encoded 00 on, that is the axis of the spin is towards the right, northeast, what is the behavior of this particle? Its behavior is characterized through rho 00. So, think of a register now. If your register has a random variable, I mean, if it's a random, it contains a random quantity whose distribution is px, just analogous to that, if you have a particle with particle and you've encoded 00 on that, and you orient that axis of spin in a particular direction, it's kind of more it's kind of described through this density operator rho 00. Okay, great. Now the key point in this talk is the following: how do you read information from a encoded particle? Right, on a register you can just read out the value. How do you read? Somebody has encoded 00 on a particle. How do you read it? Okay, and that is by what is called a measurement. And a measurement is a very key thing, and I'm going to kind of describe that in the next kind of few slides. What is a measurement? What is a quantum measurement? So I'll just give you a definition, but then I'll tell you kind of pictorially what is a measurement. So a measurement is essentially a collection of linear transforms. They are positive semi-definite linear transforms that sum to the identity. Okay, so you can always add these. Think of them as just matrices. When you add these matrices, they are positive semi-definite. They should sum to the identity. That is a measurement. Now you might wonder, okay, what is this? I mean, measurement, seems like something you go and do a measurement, right? So here on the right, I have a particle rho and I have a kind of a measurement on the left. So what do you mean by, modeling a measurement this way? So I'll explain what this is. What are these operators and what are these indices? So think of a scale, okay? These operators are essentially corresponding to the, the lines on your scale or the gradations on your scale. And these indices are like the values given to those lines. So essentially, if I have a measurement with capital K operators, I can get any of the K outcomes. Okay, and the completeness relation, in some sense, which I've written down here, they should sum to identity. You will see essentially means that you should get one of the possible outcomes. Okay, so what is a measurement? It's a bunch of linear transforms. They sum to the identity, and the indices given to these operators are essentially the outcomes you would get if you do a measurement. So think of you have a pencil or something, and how do you measure it? You have to tell me a bunch of linear operators that sum to identity, and each of those operators kind of correspond to one line on your scale. Okay, I'll kind of give you a little bit more insight into this. It seems very abstract. So what happens when you perform a measurement? Remember here on the left, on the right, I had a particle and I have a measurement. What happens when you make a measurement? So when a measurement is performed on a state, so what you do, you've prepared your quantum particle, you've taken your electron, you've oriented its axis in one direction, and then you give it to somebody. That guy can't stare at it. He needs to read information from that. So he has to create a measurement. So he'll create a measurement. What happens when he makes the measurement? So there are three things that happen, and I'm kind of going to summarize those three. First thing, you get the outcome, you get a random outcome. So the outcome is random. So even though you've prepared your particle, you have taken your particle, you sweat all your energy, and you have oriented the axis of the spin to the northeast, northeast, and you give it to your friend, and that guy measures it, he will get a random outcome. Okay. And the outcome that he gets, the probability that he gets outcome k is given by this formula, which is the trace of rho lambda k. So you just multiply rho and lambda k, and you get, that's the outcome probability. Now, if you see the completeness relation, it essentially tells you that the probability of getting one of the outcomes is 1. Okay, so no big deal. That's the first thing that happens. So first thing that happens, your outcome is random. Second thing that happens is the particle itself collapses. Okay, so the particle itself changes. It's like you measure a pencil, and the length of the pencil changes. Okay, so this is how subatomic particles behave. So the quantum system collapses to one of the following states. Okay, so remember you had a particle rho. Remember that your initial particle was rho. When you perform the measurement, it collapses to one of these states. So your particle changes. Okay, as I said in the beginning, even a benign stare at the particle kind of changes the particle. And moreover, if your scale gives you the value j, then you can tell that the state has collapsed to this state. The particle has collapsed to this state. So essentially, each of the outcomes corresponds to a possible collapses that the state can fall into. So these are the three things you have to kind of keep in mind. Okay, this is what a measurement does. All that you need. You don't need any formula, but just kind of keep in mind, when you make a measurement, outcome is random, and the system collapses, the particle changes. Okay, so now let's see, what does this imply for our quantum learning problem? Okay, so I'm again going to cartoonize this whole thing. So you have a particle, you've oriented the axis of the spin, you make a measurement. When you make the measurement, your outcome is random. So with probability 0.6, it says, okay, it's oriented that way. With probability 0.2, your outcome says, no, it's oriented to the left. With probability 0.1, it's oriented this way, and stuff like that. And furthermore, the act of measurement itself changes the particle. Okay, so that's good. So let's go to our, now we kind of have some idea of, we have to fill up that gap of what is a classifier. Remember, I talked about features being encoded on quantum states and labels being encoded on registers. And I asked you the question, okay, what is now my concept class? What should I fill up my predictors with, right? So now we have kind of an answer for that. And the answer is that you have to fill your predictors, you have to define your predictor as a measurement. So somebody gives you this quantum state, you have to measure so that you get the right label, because any observable that you have to get out from a quantum state is only through a measurement. And remember that your label is an observable, so you have to essentially design a good measurement. So you have to now equip your bag of predictors with measurements. And what you should do is choose that right measurement that can kind of give the right label to this particle. That's kind of where we are going. So the problem of function learning on a classical computer manifests itself as a learning of measurement classes. So your concept class now has a bag of measurements. You're given a bunch of training data. You have to go and identify that measurement in your bag that will label the particle correctly if you're given one without a label. That's kind of where I'm going. So you can kind of formalize this. You can write a clear mathematical statement, but I'm not going to go into that. So now let's go back to our empirical risk minimization algorithm. What did we do there? Let's try to mimic that in the quantum setting. So what did we do there? We had training data. So you had features, and you had already labeled features in some sense, and your learning algorithm was equipped with a bag of predictors, you would just compute the empirical risk for every data point. You would compute that, you would choose that function with the least empirical risk, and you would take that, right? That's what you would do. Now let's try to mimic this. I mean, the most natural thing, try to mimic this, right? So now what's your training data? It's a bunch of labeled features. A feature is a prepared electron, and your label is kind of the content in the register. It could be blue or red. I'm just making it pictorial, so you think of this as blue and red. Now your concept class is a bag of measurements. Your learning algorithm is fed with this training data. It has to go and pull out a good predictor. It has to go and pull out a good measurement. So your concept class is bag of measurements. So let's try the same thing, right? I mean, you take one measurement, you apply it on your training data, on your features. That measurement will give you a bunch of colors. You compare that with what is given. So you do the same thing with the other one, right? You make the other measurement. You get a bunch of labels. Then you see how you just count. How many of them are correct, right? And you choose the one that has more corrects or that has lesser number of errors, right? So you just go do the empirical risk. So you found that the top one is correct 3 times, the bottom one is correct only 2 times. So you choose this, right? That's what you would do with the empirical risk. But you can't do this now.
And why I have a question. Can I ask?
Yeah, please.
Yeah. So why should the labels depend upon the measurement you make? The label should be static, right?
No, the measurements are different. Just like your functions were different, your measurements are different.
Okay, fine.
Because there may be a measurement that's trying to identify the axis of spin. There may be a measurement because your feature may be encoded in a different way. So, yeah, I mean, I'm giving in this kind of a setting, I'm telling you that feature was encoded in the axis of the spin, but possibly the feature was encoded in a completely different attribute of the particle itself, and you don't know that. So you will equip your predictors with a huge class of measurements or a rich class of measurements that can decipher any feature that is there.
Okay, thank you.
Yeah, thank you. So now this doesn't work. And why does this doesn't work? Why does this not work? It's because the moment you make a measurement, the state changes. So your feature itself changes, right? So measurement alters the electron spin. So the moment you make your first measurement, your feature itself has changed. So how can you use that changed feature to evaluate the empirical risk of another measurement? You can't do that. It's not possible. So that's gone. So now you see, the things we take for granted, the feature being, not changing, itself changes. Okay, now you can say, hey, no big deal. I'm just going to make copies of the training sample. So I take the training sample. That's what you do in registers, right? You just make multiple copies of the training of the features, and then you run your function on each one of them. So I'm going to just make copies. Well, the quantum setting doesn't permit you to do that. So it turns out one of the axioms of the quantum mechanics says that any evolution of a quantum system, right? Even making a copy is an evolution. You're essentially taking 2 particles and you're creating. So you're taking, a particle that you want to kind of duplicate. So you take kind of a template register. You take the particle that you want to duplicate, and you want to ensure that both these states will be identical. That's kind of your copying mechanism. So you're kind of evolving this pair of particles. Okay. So in classical, you can make many copies of your features, or your data. Any data you can take, you can make many copies. It turns out you can't do that in quantum. So if you're prepared a particle, you cannot replicate that unless you know the particle. Okay, unless you have a good idea of what the particle is. So in other words, so I have to be careful here. In other words, there is no one way. There is no one universal copying circuit. So there is no circuit that can kind of take any quantum state and duplicate it. Remember, you're given these features, you can't stare at it. So you can't go and try to decipher what those features are before you try to copy, because the moment you try to decipher them, they change. So you have to have a mechanism that can duplicate these prepared subatomic particles without altering them. And it turns out there is no such thing. And this is what is called the no cloning theorem. You cannot clone a prepared particle. So you cannot create copies. So that implies that you're in trouble, because you are essentially looking at a blow up of the sample complexity. Why is that? Because every sample can be used to find the empirical risk of only one measurement in your class. Remember, in the empirical risk, you would take the same training set and you would blast it through every function, get the empirical risk of every function, and then you're in good shape. But here it looks like the moment you use your sample, the sample is gone. No more functions can be, the empirical risk of other functions cannot be evaluated through that, cannot be evaluated through that. So we give two ideas to actually reduce the sample complexity. In some sense, how do you do this quantum ERM? How do you reduce the sample complexity? How do you analyze? Can I get VC dimension? Can I get, can I actually learn infinite classes? So the big problem in statistical learning theory, I mean, not today, but essentially, can I have infinite classes that are learnable, right? And that's kind of your VC dimension, your Rademacher complexity, and all that. And we kind of give you notions of that. But first, we have to be able to learn. We have to be able to, improve the sample complexity. We have to be able to, in some sense, reuse samples, right? Unless we reuse samples, we are in bad shape, because forget infinite. Even if I have a finite class, I need a huge number of samples to be able to choose this empirical risk POVM measurement, right? So we'll give you two ideas. I mean, and I'll describe again these ideas through kind of simple diagrams. There is the math, but I'll not stress on that. The idea is the following. So it turns out in quantum mechanics, there is something called joint measurability. Okay, there are certain measurements that can be jointly measured. In other words, so I'll kind of again describe this. So you think of, I told you measurement is, a bunch of operators lambda. So I'm going to now have two measurements, gamma and theta. So gamma is a bunch of gamma 1 to gamma k and theta 1 to theta k. Now, as I told you, when you make this measurement, the outcome is random. So the outcome has some distribution. X comes out with some distribution px. If you make the same measurement on another particle, you get an outcome y, and y has some other distribution. Okay, so these two are two different measurements. That's why I've colored them differently. I mean, one of them is blue and one of them is yellow. Now it turns out there are certain measurements that are jointly measurable. What does that mean? There is a measurement mu whose output I can post-process classically to get x and y that are faithful to my earlier distribution px and py. So I can just run this measurement mu on my particle. It's going to give me a random variable w, and I can pass that through a classical channel and get outcomes that are faithful to what I would have got if I had just done gamma or theta. Okay, so this is the notion of joint measurability. So this clearly gives you an idea. What you do is you go into your bag and you kind of identify these jointly measurable classes. Okay, so I've just kind of written this formally in the math, but again, that's hard to understand. But even if you're interested, I'll be happy to explain later on. But this is the idea. The idea is that I can take so I call this mu as a finer measurement because it's more fine and it can be post-processed through some channels that can give you x and y according to this, that were faithful to the original measurement. Okay, so that gives you a first step at your learning algorithm. What do? Well, you have your bag of measurements. Remember, you have your concept class, a bag of measurements. You're given a training data. You are not able to use that training samples on every measurement. Now, what you do is you partition your bag into jointly measurable subsets. Okay, so you partition your entire bag into jointly measurable subsets, and in each jointly measurable subset, you can go and evaluate. You can go and evaluate the empirical risk by reusing your samples, right? So across the subsets, you can't do. So, this jointly measurable is, you give me two measurements. Sometimes they're jointly measurable, sometimes they're not. So you have to partition your bag into jointly measurable subsets. So in each subset, they are jointly measurable. Across, possibly they are not. And what you do is you partition your training samples also into corresponding subsets. So now, one subset is used for one particular subset of measurements, another subset is used for another subset of measurements. So this subset, so within this subset, within one subset, I can reuse. So I can use all of these samples all of the samples in the first kind of this set to evaluate this pink, all of the pink. So I can kind of reuse my samples there, because what I do, I go to this pink class of measurements, I choose the most fine-grained measurement, I do that one measurement on each of the samples, I get some classical output, and then I post-process it to get the output corresponding to every measurement in that bag, right? So I can kind of so I do only one measurement. That's the key. Don't do multiple measurements. Make only one measurement. And which measurement you have to do? You have to do the most fine-grained measurement in each subclass. You get classical registers, and those you post-process through some mechanism to get outcomes that are faithful to the original measurement you would have done. So that's how you do. Great. This kind of facilitates reuse of samples within a jointly measurable subset. I'm not able to do across, but I'm able to do within a subset. Great. What if your concept class is bad? What if your concept class, these subsets are really trivial, in the sense every guy is not jointly, no pair is jointly measurable. Every guy is just completely all by himself. So you cannot fine grain any pair. What do? That's bad. Then essentially this whole thing boils down to this whole thing kind of falls apart. Though it's a good nice generalization. So we'll go one more step. That's your idea 2, and the idea is the following. Again, I'm going to describe this again. Just look at the pictures. You don't have to read the math, but I'll kind of tell you what's going on. So remember, suppose I have 2 subsets of jointly measurable. Okay, so suppose I have 4 measurements. So gamma and theta are 2 measurables that are jointly measurable, and say mu tilde and gamma tilde and theta tilde are another 2 measurements. They're completely 2 different measurements that are also jointly measurable. So what does it mean? It means essentially for the first subset gamma and theta, I have a fine-grained measurement mu, which I can perform, and then I can post-process, right? And for the second subset, gamma tilde and theta tilde, I have another fine-grained measurement mu tilde, which I can kind of post-process, and I can get outcomes that are faithful to gamma tilde and theta tilde. So it's as if, so this x tilde and y tilde that are coming out is as if I had done the measurement gamma tilde, and the y tilde is as if I had done the measurement theta tilde, right? So what I do now is, okay, I have this, so this gamma and theta and gamma tilde and theta tilde are not jointly measurable in the sense I can use one particle for both gamma and theta. I can use some other different particle for gamma tilde and theta tilde, but I cannot use one for all the 4, right? And my wish is to use one for all the 4. I don't want to use, I don't want to be able to, I want to use my samples, efficiently. So the idea is the following. Let's look at mu and mu tilde. If mu and mu tilde are in some sense closed measurements, okay, they're not be jointly measurable, okay, but in some sense, if they are closed, possibly I can pull them together, okay, possibly I can kind of, possibly I can, instead of doing mu and mu tilde separately, possibly I can just do one of them, okay. So that's the idea. So what I do is I am going to pool all those fine-grained measurements that are kind of close, okay, and I'm going to pool, and I am going to do only one of them. So in other words, suppose mu and mu tilde are very close, I'm going to just choose one of them and just do one of them, and that will be a proxy for all my measurements in my class, okay. So that is the second idea: pool together closed subsets that are not jointly measurable. And if mu and mu tilde are close, pull them together, only do mu tilde. Instead of doing mu, only do mu tilde. Now, what is this notion of close? Well, that's where this mathematical formalism will come in. Essentially, the trace distance, okay, which is actually the L1 distance between the operators, have to be close. So when I add the operators of one of them and I add the operators of the other, and I look at the trace distance between them, if they are close, then I know that Px and Qx, Py and Qy are close, and I can kind of combine them. So that's where the second idea comes in. So this gives us a good kind of, so you define, when are 2 measurements close, when are 2 fine-grained measurements close, you pull them together and you do some work. So the next step of the quantum algorithm, what does it do? It essentially pools together fine-grained measurements that are close, Okay, so first step is as is. You partition your bag into subsets that are jointly measurable, but don't stop there. You then go and identify subsets whose corresponding fine-grained measurements are close. Okay, take those fine-grained measurements, look at those that are close. If they are close, you put them together. If they're far, you keep them apart. So you kind of, what you do is, in some sense, you put a net around each fine-grained measurement, you pull them together, and then you reuse within the entire net. So maybe these maybe the fine-grained measurement of the green and the red are close. Maybe the fine-grained between the pink and the gray and the yellow are close. You pull them together and you do one measurement for the entire pink, one measurement for the entire red, one measurement for the entire purple. And so you can reuse your sample. So you don't have to now divide them into 6 classes, but you can just divide them into 3 classes, and you do your same empirical risk minimization algorithm for each of these 3 classes, and you go ahead. So perform ERM in each subset, and you identify the best POVM in the subclass, and you kind of find your best ERM. I mean, essentially you divide and conquer, right? At some level, you're essentially dividing and conquering. So that is the 2 ideas for quantum ERM. So we've gone beyond this, and we have kind of characterized the sample complexity. So I have some slides telling you the sample complexity. So essentially, you choose you kind of come up with a way to reuse your samples, and then you can come up with, you can give your analytical statements. We can actually compute the sample complexity. I'm not, these are details which I'll be happy to tell if any of you are interested, but we are essentially able to characterize the VC dimension of a concept class of measurements. And if you're interested, I'll be happy to share the analytical details. So you can also get some of actually this work doesn't have everything. We have something more, but new sample complexity bound for measurability of finite concept classes, analyze learnability of infinite measurable classes via Rademacher complexity of the POVM of the measurement classes. So this is kind of the high level ideas. So I have a few minutes. I'll be happy to take questions. I can indicate some of the more recent works, but I'll be happy to take questions.
Thank you, Arun, for an informative talk. We can take a few questions. Are there any questions?
How many of you have been exposed to quantum computer or a quantum framework? Was this okay?
So I did not have any exposure to this before. Like, I've heard of it, but I never got the chance to get into it.
Okay. Yeah, it's at the intersection of 2 areas, so it's kind of difficult to. I mean, are you familiar with learning?
Yeah, I think that should be something that the audience is aware of.
Okay.
Okay,
yeah,
if there are no questions, then thank you again, Arun, for accepting
Sure.
our invitation.
Sure.
And as discussed before, we'd like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. And the link to the talk will also be posted on the webpage. Thank you and have a great evening.